Welcome to Dungeon Academics. I am Thomas and I will be your instructor. This is part of a series of videos looking at the mathematics of games and how it shapes both design philosophy and the way we play them. This is the companion video to the Fireball Fiasco, in which I will go into more details of the rather interesting maths I have used. If you're not very mathy, or still learning maths, then perhaps there will be something new for you here. On the other hand, if you are mathematically inclined, then this is my opportunity to back up the assertions I have made by demonstrating my methodology. I will cover a number of topics, ranging in difficulty, including mean, variance and standard deviation, normal distribution, continuous and discrete data, combining data sets, and the work of Abraham de Moivre. I have ordered these topics in a way that makes sense in terms of continuity, though they do tend to get more complex during the video. Many of you will be familiar with some or all of these topics, but I hope most of you will find at least something informative in the mix. By the number of faces, for this die 6. The total of the 6 faces is 21, and when we divide by 6 we get a mean result of 3.5. I know that you can't score 3.5 on a die, but this value represents all the possible results for that die. While we are here, let's do all the regular dice we might be using in our games. For a d4, the total is 10, making the mean 2.5. For a d8, the total is 36, making the mean 4.5. For a d10, the total is 55 and the mean 5.5. For a d12, the total is 78 and the mean 6.5. And finally, for a d20, the total is 210, making the mean 10.5. You may notice a pattern, that the mean for the die is always a little bit more than half the maximum result, which is the same as half the number of sides. More specifically, it can be calculated as n over 2 plus half, where n is the number of sides on that die. As long as the die are numbered sequentially, from 1 up to the number of sides, the mean, or average roll, can be found with this method: half the number of sides plus half. The next thing we have to do is look at a pair of values called variance and standard deviation. The two are related and both give a measure of how spread out the data is. A set of data with a small standard deviation will have more of its values close to the mean, whereas a set of data with a large standard deviation will be more spread out. Let's start by finding the variance. This has several steps. We'll start by calculating a value called deviance. The deviance is just how far from the mean each value in a dataset is. We can find the deviance for each value on a d6, remembering that the mean is 3.5. You'll notice that some of these values are positive and some negative. To avoid them cancelling each other out later, we shall make them all positive by squaring them. Don't worry, we will be taking the square root to undo this later. Next, we can take the mean of these squared deviances. In this case, we have 6 data entries, so we add them up to 17.5 and divide by 6. This gives us the variance. For a d6, the variance is around 2.92, but that can also be written as the fraction 35 over 12, which will be useful later. We can repeat the process for an 8-sided die. First we find the deviance for each possible value, then the deviance squared, and then the mean of the squared deviances. For a d8, the variance is exactly 5.25, or 63 over 12. Again, note that I have put this into a fraction over 12. Let's do one more, the humble d4. Following the same steps, we find the difference between each value and the mean, we square, and then we average the results. This gives a variance of 1.25, or 15 over 12. Is it always over 12? Well, yes. You may have also noticed that the numerator of the fraction is 1 less than the number of sides squared. For a 6-sided die, 6 squared is 35. We subtract 1 to get 35, and our variance is 35 over 12. Then we get to the standard deviation sets, and it is the square root of the variance. I did say we would be undoing the squaring of the deviances, and here it is. For a normal statistical distribution, and that term normal is important here, about 70% of values are within one standard deviation of the mean. This brings us to normal distribution, a statistical model that applies to groups of data where the closer values are to the mean, the more frequently the value occurs. The distinctive pattern the data makes in a frequency graph is called a bell curve, and there is a set of useful statistical tools we can do with data that follows this pattern. If we know a set of data is normally distributed, the specific shape of the curve is determined by only the mean and the standard deviation for the data. Imagine a group of people where the mean height is 175 centimeters and the standard deviation of the heights is 15 centimeters. The probability distribution of heights would look like this. Note the distinctive bell-shaped curve. If we look at the range of heights that are one standard deviation away from the mean, that is 175 centimeters plus or minus 15 centimeters, or from 160 to 190 centimeters, we can expect 68% of the population to lie within this range. 68% of the people in this population are between 160 and 190 centimeters tall. We can also expect 95% of the population to lie within two standard deviations of the mean, being 175 plus or minus 30 centimeters, from 145 to 205 centimeters tall. Every time we see a data distribution that looks like this shape, this special bell curve, we can say that it is normally distributed. There is a caveat though, and one that I perhaps have been a little bit naughty with. Data generally comes in one of two flavors, continuous and discrete. Continuous data can take any value, even if it is constrained between a minimum and maximum. A glass of milk can contain any amount of milk, from 0 to its capacity, and is not limited to distinct values. Your home, on the other hand, has a discrete number of doors, even if it is 0. A small door is still a door, and it is not reasonable to have 2.3 or 6 1/4 doors. Normal distribution can apply to both continuous and discrete values. But for discrete values, it works best when the data is finely granular. It has lots of different values to compare with. The results on 8d6 are discrete. The scores are whole numbers and no in-between values are appropriate. You can't score 28.5 damage on a fireball. As a result, some rounding is necessary, so values from 27.5 to 28.49 will all count as 28. In my previous video, I was generally comparing the spread of damage between 1 and 2 standard deviations from the mean. As the standard deviation isn't a whole number for any of these dice collections, this leads to some issues of granularity. As a result, I have had to round some values and be quite general in my results. This does not, however, change the validity of the analysis. The results of rolling multiple dice together do very closely fit a bell curve distribution and can be predicted using normal distribution rules. A critical issue for today is the behavior of multiple dice. We can investigate to find how rolling multiple dice affects the mean and standard deviation of the result. Let's start by rolling 2d6. We can construct a result table where we look at the results of the first and second roll and consider all 36 combinations of results. There are some results which should be apparent on observation. The results of 2 and 12 each appear only once in the table, scored when you roll double 1 or double 6. The result of 7 occurs the most frequently and can be found 6 times in the table. When we find the mean score on 2d6, we will have to consider how frequently each result occurs in the sample space of 36 results. I can put all of these results into a frequency table, showing how often each result occurs. To find the mean score, I'm going to calculate a weighted score for each possible result, found by multiplying the score with its frequency. As there are 3 different ways to score 4, its weighted score is 3 times 4, which is 12. We can then add these weighted scores together to find the total of all possible scores, which comes to 252. By dividing this total by the number of outcomes, 36, we find a mean score of 7. This is simply double the score of rolling a single d6. Can we simply add the means together when rolling multiple dice? Yes, that is exactly what we do. If I was to roll 8 6-sided dice, I would multiply the mean of a single d6 by 8, and 8 times 3.5 is the 28 I mentioned earlier. This also works with different types of dice. The average on a d12 is half of 12 plus half, or 6.5. So a d6 plus a d12 has a mean of 3.5 plus 6.5, which is 10. How does combining dice rolls affect the variance and standard deviation of the results? As the mean was added together, can we just add the variances, or perhaps the standard deviation? Let's find out and continue with 2d6. Remembering that the mean is 7, we can find the deviance for each score, and then the deviance squared for each result. What we have to remember is that some results are more likely than others, so we need to multiply the deviance squared by the frequency of each result to get the weighted squared deviance. We then take the total and divide by the number of possible results, 36, and we get a variance of about 5.83, or 70 over 12 in fractional form. This is exactly double the variance of a single d6. When we combine datasets, we can simply add the means together and the variances together. To find the mean and variance of 3d6 plus 2d8, we would simply add 3 times the mean of a d6 plus double the mean of a d8. We could find the variance the same way. These rules apply to all datasets, not just with dice. If we are adding the values of different datasets together, we can simply add the means and the variances. Let's look at how the values of different sets of dice look when we graph the frequencies. For a single d6, each result is equally likely. You have as good a chance to roll a 1 as a 6 or any other value. But this is not true when we roll multiple dice. For example, the 8 dice for a fireball. Let's start by looking at 2d6 again. We already made a frequency table, and the lower graph shows how this looks graphed out. Instead of a flat distribution, we now have a pyramid, with the highest point being the mean value of 7. I can build similar graphs for 3d6 and 4d6, and you can see the data evolving into the bell-shaped curve we talked about earlier. I've also drawn in the bell curve function for a perfect normal distribution. Note that this is not perfectly smooth due to the granularity of discrete data values, as mentioned previously. But the more dice we roll, and the larger the number of different results, the smoother that bell curve becomes. For these graphs, I found the frequency values using tables and spreadsheets. For 4d6, there are 6 to the power of 4, or 1,296 results to consider. For an 8d6 fireball, we would have to consider 6 to the 8th power, or nearly 1.7 million results, which is an awful lot of work, and it gets exponentially more work with each added dice. We are fortunate to be able to count on the work of Abraham de Moivre to simplify this. Abraham de Moivre was a French mathematician born in 1667. His family fled to England to escape religious persecution, and after completing his studies he became friends with Edmund Halley of comet fame and Isaac Newton, who needs no introduction. Among other things, de Moivre created this wonderful looking formula. It allows you to find the number of ways of getting score t by rolling n dice with s sides on each dice. Let's work through this for scoring 28 on 8d6. T is 28, N is 8, and S is 6. How does this all work? We can break down all the terms to see what is going on. The large Greek letter is a capital sigma. This notation is used to tell us that we may have to add together several iterations of this formula. We define a value called alpha, which has a minimum value of 0 and goes up to the value of t minus n all over s rounded down. The odd brackets around t minus n all over s tell us that we are using the floor function. Essentially, we round down any remainders. In our case, the upper value of alpha is 22 over 6, which calculates to 3.67, so we round it down to 3. We will do 4 iterations of this calculation using the values of alpha from 0 to 3, then add together those 4 iterations. The next part of the calculation is a small part that changes the sign of the calculation based on the value of alpha in that iteration. When -1 is raised to an even power, or 0, it produces a positive value, 1, so that term will be positive. But when alpha is an odd number, -1 to the power of alpha will return -1, making the whole term negative. If we take alpha is 2, we find that this term of the summation will be positive. The next component is a combination calculator, often called n choose r, but in this case n choose alpha. It asks, how many ways can we choose alpha things from a set of n options? For example, if we have 8 options, how many different ways could we choose 2 of them? This calculation takes the general form of n factorial over the product of alpha factorial and the factorial of the difference between n and alpha. That sounds awkward when spoken out, but in algebraic form it is quite simple. Remember that 8 factorial is the product of the numbers 1 through 8, 1 times 2 times 3, and so on all the way to 8. In this way, 8 choose 2 is calculated to be 28. Then we have another combinations calculation, using all the elements of the calculation. If we imagine that we are still on the iteration where alpha is 2, it would give us 15 choose 7, which is equal to 6,435. For this single iteration, where alpha is 2, we would have the value of 1 multiplied by 28 multiplied by 6,435, which is 180,180. But we have to do this for all 4 values of alpha from 0 to 3. Finding all 4 values allows us to find the sum. Note that the values alternate from positive to negative due to the first term in the summation. The sum of the 4 values is 135,954. This is the number of different ways you can roll 28 on 8d6. Remember, there are 6 to the 8th power different rolls on 8d6. Those 135,954 cases represent around 8.1% of rolls. Around 1/12 of all rolls will give 28 damage. All of this work was just to find one result on a single set of dice, but de Moivre's formula lets us find all the results on 8d6 from 8 to 48, and beyond that on any number of d6, indeed on any number of any type of dice, with the only limitation being that each die is a fair die numbered 1 to its maximum in steps of 1, and that all the dice are the same. De Moivre wouldn't be able to help us with 4d6 plus 2d8. Doing all of these calculations by hand is somewhat laborious, but with a few lines of code or a little work with a spreadsheet, the values can be calculated almost instantaneously. Calculating the exact values for the rolls of 8d6 allows us to compare the predictions made by normal distribution. The exact number of ways of rolling 26 to 30 on 8d6, that's the mean plus or minus 2, is 653,706, representing 38.9% of all the possible rolls. We know that the variance on a single d6 was 35 over 12. So on 8d6 it will be 280 over 12, or around 23.3, and thus the standard deviation is 4.83. The mean is still 28. With these numbers we can use a normal distribution calculator to predict the number of rolls between 25.5 and 30.49, which tells us that 39.5% of rolls should fall between these values. Please note, I have had to use the values that would round to 26 and 30 due to the granularity issue previously mentioned. These values are very close, 38.9% compared to 39.5%, confirming that these values are very close, 38.9% compared to 39.5%, confirming that rolling multiple dice creates a normally distributed set of results. This concludes the maths that I have done for this particular video. I learnt about the work of Abraham de Moivre specifically for this project, and it was both humbling and gratifying to find that a specific problem I had been pondering had been solved over 300 years ago by a French genius mathematician. Using his work and introducing it to a new audience has been a wonderful experience, and by doing so we are keeping the legacy of this exceptional person alive. If you have any questions or comments, please put them in the comment section below. Any requests for mathematical analysis of any game feature will be gratefully received. And as always, enjoy your next game, whatever it may be.